Hello, today we'll be covering Passage 6 out of the Science section in the First Practice ACT of the official ACT Prep Guide. For Science sections, I like to normally just skim through the passage quickly and then go to the questions to see which parts of the passage we need to read in more detail. So please pause the video and read at your own pace and examine the figures. Alright, so this passage concerns different noble gases and their wavelengths associated with them. You may not know anything about this, and you actually don't need to know anything about this because it explains everything we need to know in the passage and in the figures. So our first question, question 35, says, according to figure 2, what is the order of gas samples from shortest lambda to longest lambda for n equals 15 times 10 to the 23rd atoms? So we know we need to look at figure 2, and we know the specific point that we need to look at, which is the 15 times 10 to the 23rd point. So we'll scroll up to here, and we'll look at figure 2. This is the point we need to look at, 15, the last one, and it's asking for the shortest lambda to the longest lambda. So let's see here. The x-axis, which we've already identified the point that we need, but the y-axis here is lambda, and it goes from lowest to highest, or shortest to longest in this case. So the lowest one here is gold, and we know that's Xe, or xenon. The next lowest is Kr, or krypton. So if we're going shortest to longest, it goes xenon, then krypton. Let's look at the answers to see if any follow that order. We know it's not A and B because those start with neon, and neon is the longest one. We see C and D both start with xenon, and then the next one for C is argon, which is the orange one, not the gray one, and we've already identified that the second shortest is krypton. So the correct answer here is D. Question 36 says, according to figure 2, doubling the Ne, or neon, sample size from 6 times 10 to the 23rd atoms effectively multiplies lambda for neon by a factor of, and then we have a few options here. So let's unpack what this question is asking. We know we need to look at figure 2, and it's saying if we double the sample size for 6 times 10 to the 23rd atoms for neon, how does lambda change? So let's scroll up and see what the current value is for 6 times 10 to the 23rd for neon. So we have 3, 6, 9, 12, 15. Here's the 6. We go down to the legend to see which one is neon, and it's the blue one here. So 6 in blue, it's right around 1600 lambda. But if we double it, and we go to 12 instead, then lambda becomes around 800. So if we go from 1600 to 800, and it's asking for the multiplicity factor, what does that mean? So 1600 to 800 you divide by 2 or multiply by 1/2. We look at the available options and we see that G is the correct answer, 1/2. Question 37 says, consider 2 krypton samples at 293 Kelvin, each with N equals 6 times 10 to the 23rd atoms, but one with V equals 25 liters and the other with V equals 50 liters. Based on figure 1, lambda for the 50 liter sample will most likely be how many times as great as lambda for the 25 liter sample. So they threw out a lot of numbers here in a few different units, but let's see what we actually need to know to answer this question. So it's saying, based on figure 1, so we can go over to figure 1, take a look here. It's asking about lambda for 25 liter and 50 liter samples for krypton. Okay, so krypton is the gray one, and the 25 liter, because we look at the x-axis here, says V for liters, and then we have 25 right here is the gray one. If we doubled the volume to 50 liters, how big would this get? Well, it's asking for just a rough idea, so it's just asking for kind of the multiplicity factor. And so this appears to follow a linear relationship. So if we doubled V, went up to 50, it follows that lambda would also double as well, because this trend is very nice, it's a straight line. So if we continue the straight line beyond over here into this question, it looks like lambda would just about double. So based on that, how many times as great would lambda be for the 50 liter sample as opposed to the 25 liter sample? It would be about 2 times as great. So the correct answer here is C. Question 38 says, based on figure 1, for the xenon and argon gas samples with V equals 20 liters, compared to lambda for xenon, approximately how much longer is lambda for argon? Okay, so let's unpack this here. It's saying figure 1, so we can scroll up and look at figure 1 here. It's asking about xenon and argon gas samples at V equals 20 liters. So at the bottom here we find our relevant V, and we see here is the 20. And it's asking about lambda for argon and xenon, and how much longer is the lambda for argon versus the lambda for xenon. So here is 20, and we look down, xenon is the yellow, that's the bottom one here, and AR or argon is the orange one here. That's this top one here, not the very top one, but this top in the group of 3. It's asking approximately how much longer is lambda for argon. So we take visually the orange minus the yellow. Well, it's kind of tough to see because you can't really see how much that means. But let's take a look at the yellow and follow on over and see where the lambda meets up with the coordinate axis, and it's just under 200. But let's look at orange now and follow it on over here, and it's just under 400. So if we take around 400 and subtract around 200, we can see the distance from the yellow to the orange here, and that's around 200 nanometers. So the correct answer here is J. Alright, question 39 says, the collision frequency is defined as the number of collisions between gas atoms per second. Consider the 5 liter and 25 liter xenon samples represented in figure 1. Assuming the xenon atoms have the same average speed in both samples, in which sample would the collision frequency most likely be higher? Okay, so we defined a new phrase here, the collision frequency, and that's the number of collisions between gas atoms per second. We're looking at 2 different samples. One is smaller than the other in terms of volume, and we're assuming that they have the same speed in both samples. Then we're trying to figure out in which sample the collision frequency is higher. So the collision frequency is the number of collisions per second. So if we scroll on up here and look at figure 1, which was referenced in the question, we see that the mean free path, or lambda, is smaller for the 5 liter case, and it's larger for the 25 liter case for all of them. We're looking at xenon in particular, but it holds true for all of them. So what does this mean? This means that when there is a smaller volume for the gas particles to move, they collide in a shorter distance. This makes sense because you can imagine trying to be in a small room and imagine your gas particle so you can just walk in a straight line, and you go until you hit another gas particle. You run into many more gas particles in a small room than a really, really large room. So based on that, let's scroll back down to the question. In which sample would the collision frequency most likely be higher? Well, given that the mean free path is lower in the 5 liter sample than the 25 liter sample, and we're assuming that the gas particles are moving at the same speed in both samples, it makes sense that the 5 liter volume has more collisions per second. Therefore, the collision frequency is higher. So let's take a look at the answers here. We see A and B say the 5 liter sample, and C and D say the 25 liter sample. Those ones are wrong. So we can just cross those out right here. So A and B may both be right, but let's look at the details. A says xenon atoms in the 5 liter sample travel on average shorter distances between collisions, therefore collide more often, or they travel longer distances between collisions and therefore collide more often. Well, maybe you intuitively know what this means, but we can also scroll up and just double check our logic here by looking at figure 1. Okay, just to recap, the 5 liter one has a shorter mean free path to collision than the 25 liter one. So let's scroll back down and look at the options again. Shorter distances or longer distances? Okay, we know that it has shorter distances in the 5 liter sample, so A is the correct answer. Our last question, question 40, says, for a particular sample of radon gas in a 25 liter container at 293 Kelvin, lambda is approximately 320 nanometers. If D for radon is 0.240 nanometers, then, based on Table 1 and Figure 2, approximately how many radon atoms are most likely in this sample? Okay, so this question is kind of a doozy here. We're introducing a new gas here, radon. It's in a certain size container at the standard temperature, so that's okay. It gives us a lambda value and the D for radon. And we have to consult Table 1 and Figure 2. We're going to have to do some scrolling here. So let's look at the D for radon is 0.24 nanometers. If we scroll on up to the table, we can see that neon has a much smaller diameter, argon is a little bit bigger, krypton is bigger, xenon is bigger, but all of them are less than radon. So if we scroll back down, and we can confirm that 0.24 is indeed greater than the largest one, 0.216. So that means that radon has a larger diameter than all of the other gases present in this study. Lambda is approximately 320 nanometers in this case. Okay, so if we scroll back on up here, and we go to Figure 2, and we look at, okay, so we have xenon as the lowest here is yellow, and neon is the highest here. Neon is the smallest, and xenon is the largest D. We can see that as we increase D, or diameter, we seem to go down in this chart. So here's the smallest diameter, and then we increase, increase, increase. So if we go even past xenon and go down here where radon would be, we can kind of trace out where we think it would be. So in this case, it might be somewhere in here, because each of them seem to decrease as we increase diameter. So if that's the line for radon, as we kind of suspect based on this trend, and it has 320 nanometers for lambda, we can trace out here, alright, here's about 320-ish, and we go on over, and maybe it's going to be somewhere in this area. It's just kind of a rough estimate, and it may be between 3 and 6 times 10 to the 23rd atoms. So we'll scroll on down and take a look at our answers. I'm going to clear this right here. And we need to know approximately how many radon atoms are most likely in this sample. We have a few options here: less than 6, 6 to 9, 9 to 12, or 12 onward. And we'll scroll on up, and unfortunately I cleared it, but remember that the line was here, and it intersected, maybe somewhere around here for 320 nanometers for lambda. So we can conclude that, based on the binning, it's either less than 6, 6 to 9, 9 to 12, or 12 or greater. It looks like 6 or less is how many atoms are in that radon sample. If we scroll on down, we see that the correct answer is indeed F, 6 times 10 to the 23rd. I'll quickly recap what we've covered in this passage. It dealt with a few different gases, and their diameters, and their mean free path of collisions. And in this passage, we had to kind of look at two different graphs, which showed parts of the same info, but actually very different amounts of info in each. Each question only referred to one of the figures. It never had you refer to both of them at once, but some of them refer to the table and a figure. And in this case, a lot of it just involved tracing where the data points were on the figure to a certain axis, and then interpreting that correctly. I hope this helped, and thank you for watching.